So welcome viewers in the lecture series for the course BSM 101 Mathematics 1 under AICTE and course code BSM 102 Mathematics on B under Maulana Abul Kalam Azad University of Technology. So in today's lecture 2 we will establish the formula for radius of curvature in different coordinate systems. So to do that, let us go through the following figure where in the curve FPQ, suppose we have to find the radius of curvature at the point P, of which Cartesian and polar coordinates are xy and r theta respectively. Also, we will assume that the tangential angle at P is psi and the perpendicular distance from origin to the tangent at P is small p. Now, to proceed further, we will consider a point Q on the curve which is very close to P, and accordingly its coordinate parameter will vary a little bit than that of P, which is expressed here. We also further draw perpendicular PT to the radius vector of Q OQ and assume that the angle between the radius vector at P and the tangent at P is phi, while the line joining PQ makes angle alpha with the extended radius vector at P. So with this assumption, let us start our discussion. So from the triangle PLQ, what we can observe, as Q approaches to P, then the arc QP, the arc wall distance QP, which is equal to delta S, where S denotes arc wall distance from the fixed point F on the curve to P, and S plus delta S is the arc wall distance of the point Q from the fixed point F. So delta S, which is the arc wall distance PQ, it will be same as the linear distance among PQ, because when Q is close enough to P, we can consider the portion of that curve PQ to be a straight line, which is by Pythagoras theorem equal to PL square plus LQ square. Now PL square plus LQ square is delta x whole square plus delta y whole square. That is, as Q approaches to the point P, we have delta S square whole square is same as delta x whole square plus delta y whole square. So from here we can write that as Q approaches to P, then delta x will approach to 0. So we can write the above equation as limit delta x goes to 0, delta s delta x divided by delta x whole square is equal to 1 plus limit delta x approaches to 0, delta y by delta x whole square. So which turns out to be ds dx whole square is equal to 1 plus dy dx whole square, which further reduces to ds whole square is equal to dx whole square plus dy whole square. So call this equation to be equation A. Now we have another triangle to consider. So before going into that, as Q is very close enough to P, that means delta theta is very small, and for that From triangle OPT, we have PT is equal to R sine delta theta, but as delta theta is very small, so this will be equal to R times delta theta, while OT will be R cos delta theta, but as delta theta is very small, so cos delta theta will be 1, so this is equals to R. Therefore, TQ will be OQ, length of TQ will be OQ minus OT, which is R plus delta R minus R, which is delta R. So as Q approaches to P, from the triangle PTQ, we have delta S, which is the arc distance of the arc PQ. This will be equal to the linear distance PQ if Q is very close enough to P, and by Pythagoras theorem it will be equal to PT square plus TQ square, which further turns out to be PT is R del theta whole square plus TQ is delta R whole square. So that is, as Q approaches to P, we can write this further as delta S whole square as R delta theta whole square plus delta R whole square. Now see, when Q approaches to P, in that case delta R also approaches to 0. So the above equation can be expressed as limit delta R goes to 0, delta S by delta R whole square is equal to R square limit delta R goes to 0, delta theta by delta R whole square, which further reduces to ds dr whole square plus on will be there. We are dividing by delta R square. So ds dr whole square is equal to R square d theta dr whole square plus 1, which can be further expressed as ds whole square dr whole square plus R square d theta whole square. Call this equation B. So if we combine these two results A and B, so we can, combining A and B, this gives that ds square whole square is same as dx square plus dy whole square, and which is same as dr square plus R square d theta whole square. Now we will proceed further, that if you observe carefully, you will observe that the angle PQT, it is alpha minus delta theta. Therefore, tan of alpha minus delta theta, this will be simply perpendicular by base, that is R delta theta divided by delta R. Now see, as Q approaches to P, then QP, the line joining Q and P, tends to become tangent at P, and hence the angle alpha tends to phi. Why? Because alpha was the angle between the line joining PQ and radius vector. Now if the line tends to be their tangent at P, that means now alpha is denoting the angle in between the tangent at P and the radius vector, which is phi, as per our assumption. Hence, as Q approaches to P, then alpha tends to phi, and also delta R, this approaches to 0, as well as delta theta approaches to 0. So the above equation star reduces to tan of phi is equal to r d theta dr. So call this as equation number 1. It will be used here. So from here we can write that the value of sin phi to be r d theta divided by root over dr whole square plus r d theta whole square, which turn out to be by result 1. This is nothing by r d theta ds, and similarly cos phi will be dr ds. So call these three result by 2. Also, if we observe carefully in this figure, we will observe that the perpendicular distance P from the origin to the tangent at P, that is length of ON, which we have assumed to be P, this is nothing but OP sin phi, and OP is, that is R, and value of sin phi is, or we can write this like this, R into R d theta ds, that is R square d theta ds. And from here what we can write that 1 by p square is equal to 1 by r square, because OP is R, cosec square phi, and cosec square phi is nothing but 1 plus cot square phi. Now from 2, if we put the value of cot phi to be ds by r d theta, so this turns out to be 1 by r square into 1 plus 1 by r square dr d theta whole square. So which further reduces to 1 by r square plus 1 by r to the power 4 dr d theta whole square. So call this as equation number 3. So these three results will be the building blocks for finding out the expression for radius of curvature at a point on a curve in different coordinate systems. So let us go into that. So first assume that the given equation is in pedal form. That means pedal equation. So by pedal equation we means a curve where the equation among the perpendicular from origin to the tangent vector, that is P, and the radius vector is given. P is equal to say f of r. So for this kind of equation we will find out the expression for radius of curvature. So as you can see from the figure that angle psi will be sum of the angle theta and phi, because the external angle is same as sum of the opposite internal angles. So that means in this case psi will be theta plus phi. So from here what we can observe that d psi ds, this will be d theta ds plus d, instead of writing directly d phi ds, we can use the chain rule here. So d phi dr times dr ds, this we can do using chain rule. Now from result 2, d theta ds is nothing but sine phi by r, and d phi dr ds is cos phi into d phi dr. So we can take 1 by r common from here, and this will become sine phi plus r cos phi d phi dr. So which can be expressed further as 1 by r d dr of r sine phi. But if we recall, r sine phi was nothing but p, so that means 1 by r dp dr. So this is the value of curvature, because curvature was d psi ds, so imply rho, which is 1 by curvature, that means 1 by d psi ds, or we can directly write this as ds d psi, this will be r dr dp. So see how using those building blocks we found out the radius of curvature rho for pedal equation. In similar way we can find out for different equations. Say for we have the equation in Cartesian form or Cartesian equation. That means Cartesian equation is in generally expressed as y as a function of x. So for this, what we know, that tan psi is equal to dy dx, right? From here, if we differentiate both sides with respect to x, what we'll get? Sec square psi d psi dx, this will be y double dash, that is d2y dx square. Now sec square psi is further written, can be written as 1 plus tan square psi, that means 1 plus y dash square into d psi dx is equal to y double dash. Now radius of curvature, which is rho, we know that its value is ds d psi. Okay, so this can be written as ds dx times dx d psi using the chain rule. Now what is the value of ds dx? If you observe result A, then from here you can write what is the value of ds dx. This is nothing but root under 1 plus y dash square. So from result A, ds dx is nothing but root under 1 plus y dash square, where y dash is on dy dx. And what is dx d psi? From the previous result, from here, what is the value of dx d psi? This will be 1 plus y dash square divided by y double dash, provided y double dash is not equal to 0. So the expression for radius of curvature in the Cartesian equation turns out to be 1 plus y dash square whole to the power 3 by 2 divided by y double dash, where y double dash is not equal to 0 and y dash represent dy dx and y double dash is d2y dx square. And suppose in the Cartesian equation of a curve, instead of the function y is equal to fx, it is given in the form x is equal to fy. Then by similar kind of construction, we can show that the radius of curvature, expression for radius of curvature will be also of the similar form 1 plus x dash square whole to the power 3 by 2 divided by x double dash, where x dash is in this case dx dy and x double dash is d2x dy square, and we assume that this does not vanish. So for these two kind of equation we have formulated the expression for radius of curvature, but there are other several coordinate system by which a equation of the curve can be expressed. So instead of proving all those results, we will only give the expression for radius of curvature for in those system, which can be found out using these three building blocks which we have proved. Okay, so I am not going into the detail of those proof. We will just discuss the expression for radius of curvature. So what are those expression? Let us name these results. Call this A, the pedal equation. For the Cartesian, call this to be B. Then suppose we have the parametric equation. So what is parametric equation? So parametric equation means say x is equal to say f of t and y is equal to say g of t. In this kind of case, what will be the expression for radius of curvature? This will be simply x dash square plus y dash square whole to the power 3 by 2 divided by x dash y double dash minus y dash x double dash, where x dash means this is dx dt, which is basically f dash t, and y dash is dy dt, which is basically g dash t, and x dash y double dash minus y dash x double dash that not vanish. This will be our assumption. So this can be also proved using those three fundamental results and the previous establishments. So we are not going into the detail of the proof. Now suppose the equation is in implicit form. That means implicit equation, where the equation of the curve is expressed in this form: function of xy is equal to 0, where neither x nor y can be written as a dependent variable to the other. So in this kind of case, the expression of radius of curvature rho will be fx square plus fy square whole to the power 3 by 2 divided by fxx fy square minus 2 fxy fx fy plus fyy fx square. See, the denominator is symmetric, where the denominator does not vanish. That means it is not equal to 0. So the point at which we want to find the radius of curvature, at that point the denominator should not vanish. Otherwise, this formula would not work to find radius of curvature at that point. So what is fx here? Fx is nothing but partial derivative of f with respect to x. Fy is partial derivative of f with respect to y. And similarly the other things. For example, in this case fxy is del y of del f del x. Okay, and so on. So for implicit equation we have also given the expression. Now suppose the equation is given in polar form. Polar equation means r is a function of theta. In this case, what will be the expression for radius of curvature? In this case, the expression will be r square plus r1 square whole to the power 3 by 2 divided by r square plus 2 r1 square minus r2, where r1 is nothing but dr d theta and r2 is nothing but d2r d theta square, and here also the denominator r square plus 2 r1 square minus r2 does not vanish. This will be our assumption. There is more kind of equation which is known as tangential polar equation of a curve. Tangential polar equation. So in this kind of equation, there is a relation in between the tangential angle psi and the length of perpendicular from origin to tangent, which we have denoted by P. So in this case, P is denoted as a function of the tangential angle psi. So for this kind of equation, what will be the expression for radius curvature rho? This will be simply P plus d2P d psi square. Okay. And if we have one more intrinsic equation, so intrinsic equation means it has direct relation between the arc distance from a fixed point on the curve and in between the tangential angle psi. So in this kind of case, the radius of curvature will be directly ds d psi, that means f dash psi, and we have to plug the point psi at which we want to find out the radius of curvature. So with this discussion, let us do few problems to find out radius of curvature. So example 1, find radius of curvature of the ellipse x square by a square plus y square by b square is equal to 1 at an arbitrary point xy. Okay, so we can use the implicit formula here, but we can try in Cartesian form also, because from this equation we can find out x and y in terms of the other variable directly. So we will use that formula. Someone can use the formula for implicit form also. In that case, fxy will be x square by a square plus y square by b square minus 1, which will be equal to 0. Okay, so we will use the Cartesian formula. So for that we need the value of y dash. For that we derivative the equation with respect to x, so which will give us 2x by a square plus twice y by b square into y dash is equal to 0, which implies that y dash is minus b square x by a square y. So from here, if we try to find the double derivative y double dash, this will be minus b square by a square into y square y into 1 minus x into y dash. Value of y dash is again minus b square x by a square y. So which is minus b square by a square. In the denominator, if we multiply by a square y, then it will become a square y cube into a square y square plus b square x square. Okay, so now 1 plus y dash square value is 1 plus b to the power 4 x square divided by a to the power 4 y square, which is a to the power 4 y square plus b to the power 4 x square. So if we take power 3 by 2 on the both side, so this will be whole to the power 3 by 2, this will be whole to the power 3 by 2, which is turns out as denominator will become this is a square y whole square, so square will cancel out, so cube, so this is basically a to the power 6 y cube, and the numerator will keep as it is, a to the power 4 y square plus b to the power 4 x square whole to the power 3 by 2. Therefore, rho will be this expression star, because this was in the numerator, divided by y double dash. So this will be basically a to the power 4 y square plus b to the power 4 x square whole to the power 3 by 2 divided by a to the power 6 y cube into minus, we can plug it here, minus a to the power 4 y cube divided by b square into a square y square plus b square x square. So y cube will get cancelled out, a to the power 4 will also get cancelled out. So this is minus a to the power 4 y square plus b to the power 4 x square whole to the power 3 by 2 divided by a square b square into a square y square plus b square x square. Now see, as the point xy lies on the ellipse, so that means it will satisfy the equation of the curve. So that means as xy lies on this ellipse, so that means b square x square plus a square y square, this will be equal to a square b square. So value of this expression is always a square b square if the point xy lies on this curve. So this we can substitute here in the denominator. So this will turn out to be minus a to the power 4 y square plus b to the power 4 x square whole to the power 3 by 2 divided by a to the power 4 b to the power 4. Okay. Now see, the minus symbol which comes here, it actually denotes the direction in which the radius or center of curvature lies. That means what? Suppose this is the curve and we are trying to find out radius of curvature at this point. Of course in this direction. But suppose the curve is like this. Then if we measure the direction, so in this case the radius of curvature will be in this direction, in the direction of bending. But if we measure positive length in this direction, then this will be negative length, right? So whatever is the expression of radius of curvature, we can always only consider the magnitude, because we are only concerned about the value of the radius of curvature. So considering the magnitude only, rho will be a to the power 4 y square plus b to the power 4 x square whole to the power 3 by 2 divided by a to the power 4 b to the power 4. So I think the idea is clear. Then let us do another example. So find radius of curvature at the point s comma psi of the curve of which intrinsic equation is given as s is equal to a sec psi tan psi plus a log of sec psi plus tan psi. Okay, so this is the easiest one. So in this case, directly radius of curvature rho is nothing but ds d psi. So we will take derivative with respect to psi, and which turns out to be a into sec psi, then derivative of tan psi is sec square psi plus tan psi into sec psi tan psi plus a log of x, that means 1 by sec psi plus tan psi, then multiplied derivative of sec psi plus tan psi, which is sec psi tan psi plus sec square psi. So which if you simplify, we will obtain that this is, from here we can take sec psi common, so this will become sec square psi plus tan square psi, and the second expression, if we take sec psi common from the numerator, remaining portion will get cancelled out, so this is simply a sec psi. So if we take a sec psi common from both this expression, this will be 1 plus sec square psi plus tan square psi. Now 1 plus tan square psi is again sec square psi, so this is a sec psi into sec square psi plus 1 plus tan square psi, that is sec square psi. So this simply turns out to be twice a sec cube psi. So this will be the radius of curvature at the point psi. So with this problem we will conclude this lecture 2.